Today I'm going to be talking about biodegradable polymers. But before I get into the nitty-gritty details, we first have to cover the basics about polymers. So, what is a polymer? A polymer is a large molecule or a macromolecule formed by linking small units, monomers, through polymerization. You have monomers, where there's one unit, dimer, 2 units, trimer, 3 units, and so on, until you get a polymer where there's n number of units. So there's two types of polymerization. The first one being chain growth polymerization, where monomers are added one by one at the end of a growing polymer chain. And then there's step growth polymerization, where both monomers and growing chains have reactive groups, and therefore all species can join to form longer chains. So, what affects the properties? The molecular weight of the polymer and the individual molecular weights of the monomers can be used to calculate a number and a weighted average molecular weight. The number average molecular weight, Mn, equals the sum of the mass of each chain divided by the number of chains. The weighted average molecular weight, Mw, equals the sum of the mass of each chain squared divided by the sum of the mass of each chain. Two populations with the same Mn may have a very different Mw, which would change the properties. Dispersity is the weighted average molecular weight divided by the number average molecular weight. The closer the dispersity is to 1, the greater the proportion of polymer chains with the same length. The lower this value, the lower the value of the physical and mechanical properties. The properties are also affected by the functional groups of the monomers, which can affect the strength of the intermolecular forces, such as hydrogen bonding due to the presence of OH groups, the chain length and branching, the stereochemistry, whether it's isotactic with the same stereochemistry, or atactic with alternating stereochemistry. So, copolymers. A copolymer is a polymer that contains two or more different monomers, which allows us to mix the properties of separate monomers. Ethylene and vinyl acetate can form a copolymer of polyethylene covinyl acetate. It's waterproof due to its crystallinity and the cross-linking density. It's used in shower curtains. It's formed through radical chain polymerization at high pressure. An example of a polymer is polyethylene. Its monomer is ethene. It's a versatile material used in the formation of plastics, which are utilized in a large range of products, such as bags, bottles, toys, and even bulletproof vests. As a result of the many uses of these plastics, they have been mass-produced, and therefore the amount of refuse created has increased exponentially. There are 3 types of polyethylene. Branched, low-density polyethylene, which is cheaper and easier to make, and is also more flexible, which is used to make things like cling film. Then there's linear, high-density polyethylene, which is stronger and used to make plastic containers. Then there's ultra-high molecular weight polyethylene, which is used to create fibers which can replace Kevlar in bulletproof vests. This shows just how much molecular weight affects the properties of polymers. LDPE and HDPE are between 200,000 and 500,000 monomer units, but UHMWPE is between 3 and 6 million monomer units. Plastic. Yes! Due to it being inexpensive, strong, flexible, resistive, chemically inert, and versatile, plastic is used in a multitude of industries. But it has to go and ruin this. Plastic. Boo! Synthetic polymers are manufactured from crude oil, and of course there is only a limited amount of crude oil available, so we should find other processes of producing polymers. Unfortunately, because of their chemical inertness, they are non-biodegradable, therefore there is a lot of plastic waste. Garbage Island. The Great Pacific Garbage Patch is the largest of 5 plastic accumulation zones, which is mostly comprised of non-biodegradable microplastics. It's estimated to be 1.6 million square kilometers, which is 3 times the size of France, that baguette place, and it continues to grow, which of course has had an adverse effect on any marine life. It poses entanglement risks. Animals confuse the plastics for food, causing malnutrition and bioaccumulation, which is where the chemicals from the plastics enter the food chain and then can affect humans, because we'll eat the fish. Biodegradable polymers. I told you we'd get to the nitty-gritty. These are polymers that degrade via enzymes and or hydrolysis reactions, leading to the production of carbon dioxide and water. They can be used in targeted drug delivery, including in chemotherapy, automation to create lighter vehicles that require less fuel, construction and electronics, surgical implants, and as a replacement for plastic bags/packaging. There are 2 types of biodegradable polymers: synthetic, which typically contain ester linkages, so bond cleavage occurs via deesterification, and natural, which includes polysaccharides, proteins, and lipids. Degradation occurs through enzyme action secreted from microorganisms and or hydrolysis reactions. And here is an image detailing how an enzyme breaks down a substrate. So, what are the advantages of these biodegradable polymers? Well, they produce less carbon dioxide gas when degraded. Due to degradation, there will be no buildup of litter, so there is less of an impact on wildlife and less land will be required for landfills. And many are produced from renewable materials. However, there are disadvantages. Microplastics can still be produced from their degradation. Degradation requires specific microorganisms. There's limited biodegradation in aquatic environments. Land being used for feedstock isn't being used for food. And degradation in anaerobic conditions produces methane gas, which is a greenhouse gas and will therefore contribute to global warming. An example of a natural biodegradable polymer is starch thermoplastics. So you take native starch, which is a long-chain carbohydrate which can be obtained from corn, wheat, or potatoes, and then plasticize it using heat/pressure, causing starch gelatinization. This is an order-disorder transition. You can use polyglycols, amides, or amines as non-volatile plasticizers. It's then homogenized and melted in an extrusion process with a plasticizer, which causes a permanent conversion to a thermoplastic starch that is free of crystalline fractions. Starch thermoplastics can be used as a raw material in film production, which can be applied to disposable food serviceware, food packaging, bags, and loose fill products. Furthermore, it can be used as a filler in LDPE. So when microorganisms break down the starch, it becomes porous, allowing for the rapid saturation of oxygen and microorganisms. This causes degradation via biological and oxidative pathways. Microorganisms will produce amylase, which will bind to starch, placing stress on the bonds, making bond cleavage easier. The properties include low thermal stability, high water vapor permeability, biodegradable, good oxygen barrier, not electrostatically stable. PVA and PVOH. Polyvinyl acetate, PVA, is formed through the free radical polymerization of vinyl acetate monomers. It's used as an adhesive and can form an ABC copolymer of vinyl acetate, ethylene, and vinyl acetate ethylene. It's used in paper coatings, paint, binder and glass fibers, sanitary napkins, and filter paper. Degradation occurs via base hydrolysis of PVA ester groups, forming polyvinyl alcohol, PVOH, and acetate, followed by controlled oxidation or enzyme action, secreted from microorganisms. PVOH can be used to form a moisture barrier film for foods and food supplements. Chloronic copolymers. These are polymers that consist of two different monomers. One is hydrophilic polyethylene oxide, which we will call A, and the other is hydrophobic polypropylene oxide, which we will call B. This makes it both hydrophobic and hydrophilic, and it's therefore amphiphilic. They have a low in vivo toxicity. It's an ABA block copolymer synthesized through the controlled polymerization of one monomer followed by a chain extension of the other monomer. So, chloronic copolymers, what can we use them for? Well, I'll tell you, drug delivery. Due to their amphiphilic nature, chloronic copolymers can form a micelle with a hydrophobic center and a hydrophilic corona, or edge, which can then hold a drug. Specific polymers can be chosen so that the degradation occurs at a target site. The enhanced permeability and retention effect, which occurs because of the high blood vessel permeability in tumours, allows for a passive drug targeting route in anti-cancer chemotherapy. Well, that's all, folks. I hope that today has shown you how instrumental polymers are to our modern world, and the necessity of making and implementing more biodegradable polymers. If you would like to read about biodegradable polymers yourself, you can take a look at my sources shown in the next slide. Thank you for listening.